So what if we're taking the derivative of two functions that are dividing each other? So we have a function in the numerator and a function in the denominator. So our rule goes, we take our function from the denominator times the derivative of the function from the numerator minus function from the numerator times derivative of the function in the denominator, all over that denominator function squared. So memorizing this is real tough. Again, put this on a little note sheet somewhere so you can refer back to it. With this one, order is very important because in the numerator we have subtraction here, so it has to go denominator times derivative of a numerator first. So you can't switch those up here. A common little, I don't know, there are all sorts of little songs that go to this too, and now thankfully you don't have to hear me sing because I can't remember any of them, but they're out there. So if you think of this as you're taking the derivative of high over low, how it will go is low d high minus high d low all over low low. I think it goes to like row 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 your boat, but again, I'm not gonna try that right now. But just a little phrase to help out with it. So let's try this out. I'm going to do the same thing that I did with the product rule of kind of taking a case. Ooh, I did this incorrectly. 1 second. I'm going to change that denominator to x squared. Okay, a case where we don't really need the quotient rule, but we can compare and contrast and see how this works and get a nice little simple example to start with before we jump into the more complicated ones. So finding the derivative of x to the fourth, just using the power rule. So if we have x to the fourth, the derivative, so exponent of 4 multiplies with x to the 4 minus 1, which is 3. And we're done, yay! But how we could also represent this is x to the 6th power over x squared. So using our rule of exponents, it would be 6 minus 2 would get us to that exponent of 4. But let's go ahead and work with this. If our function had that form, in fact, let's go ahead and write this here. F of x equals x to the 6th over x to the 4th. And we want to find the derivative. So I'm going to go ahead and use our little tune. So we have high and low. So I'm going to take low d high, so x to the 4th times the derivative of that numerator function, x to the 6th, minus high d low, so x to the 6th times the derivative of x to the 4th, all over low low, so we're taking x to the 4th, and we're squaring it. All right, then it's just a matter of simplifying. I'm going to go ahead to this right-hand side here. So we have x to the 4th times the derivative of x to the 6th power, so that's going to be 6x to the 5th. And then we'll have minus x to the 6th times the derivative of x to the 4th, which is 4x cubed, all over x to the 4th squared. And with the power rule, you multiply those together. So it's going to be x to the 8th power. All right. Next line. Let's see, x to the 4th times 6x to the 5th will be 6x to the 9th. So you add the 4 and 5 together, minus 4x to the 9th, all over x to the 8th. And up in that numerator, we're getting 2x to the 9th over x to the 8th. What did I do? I know you have those days where you just make the same mistake twice. Okay, I accidentally wrote x to the 4th here. And it should be x squared. So I'm just going to make some adjustments. Sorry, that denominator should have been x squared. So we're taking, I knew we were headed somewhere incorrectly with that last step there. All right, so x squared times 6x to the 5th minus x to the 6th times the derivative of x squared should be 2x all over x squared squared, so 2 times 2, x to the 4th. Okay, one more time. So this will be 6x to the 7th minus 2x to the 7th all over x to the 4th, which is 4x to the 7th over x to the 4th, which will be 4 times x, and then with the exponents, a 7 minus 4 leaves us with a 3. And there we go, 4x cubed. Hooray! So that's our process for using the quotient rule. So let's try this out. 2 examples. All right, f of x equals 5x squared minus 1, so that's going to be my high function. And then over 2x cubed plus 3, that's going to be my low function. So the derivative is low d high, so 2x cubed plus 3 times the derivative of 5x squared minus 1 minus high d low, so 5x squared minus 1 times the derivative of 2x cubed plus 3 all over low, so 2x cubed plus 3 squared. Now, my suggestion is, because sometimes we'll get things that cancel out, leave the denominator factored out. Like I'm not gonna FOIL this out yet. I'm actually gonna keep this as factored as possible in case I can see something that cancels out in the work later on. So after you do this, your focus is really on the numerator and simplifying the numerator. All right, so simplifying the numerator, we're going to have 2x cubed plus 3 times the derivative of 5x squared minus 1, which really is just the derivative of 5x squared, which is 10x. And then we're going to have minus, we're going to need to keep these parentheses here because of that subtraction. Super important. 5x squared minus 1 times this derivative of 2x cubed plus 3, which should be a 6x squared. All over, and we're just going to keep that the same. 2x cubed plus 3 squared. All right. Oh, I have more space to the right. Well, let's keep going. Equals. Okay, we're going to distribute that 10x in. So that's going to be 20x to the 4th plus 30x. And then minus, I'm going to keep parentheses here while I distribute the 6x squared. So let's see, that'll be 30x to the 4th. And then minus 6x squared. Again, keeping the denominator exactly the same. And now I'm going to distribute that negative in. So that's why I needed to keep those parentheses there. So we're going to have 20x to the 4th plus 30x minus 30x to the 4th and plus 6x squared all over 2x cubed plus 3 squared. All right, let's see. We have combining like terms, 20x to the 4th minus 30x to the 4th, so that's a negative 10x to the 4th plus 30x plus 6x squared. Yep. All right, 2x cubed plus 3 squared Then I'm going to look for something that I can factor out. So I can factor out a common factor of 2. I could even make it a -2. You can also factor out an x. So let's go ahead and do a -2x, which will leave us with 5x cubed. I'm going to move the 6x squared over, so that'll be a -3x, and then -15, all over 2x cubed plus 3 quantity squared. And that's going to do it. We're going to get stuck there with that cube right there. Yep, we're done. Some of these, using the quotient rule, will just cancel things out so nicely and get so simple, and you can get the feeling that it's right. And then there are ones like this where you get to the end and you're just like, is that? I don't know, it's so messy. But hey, that's how mathematics is sometimes. It's not always gonna be pretty. So with that, it's a matter of applying the rules correctly, showing your work, taking your time with it too, especially with negatives and these exponents. Just slow and steady wins the race with these for sure. Okay, one more example here. We're going to find the equation of the tangent line. So we're finding y equals mx plus b. We have our coordinate, and we have our function, 4x over 1 plus x squared. Okay, so we want to first find the slope, and with that we need to take the derivative. So 4x is going to be my high function, 1 plus x squared is going to be my low function. Taking the derivative, we start with low d high. So 1 plus x squared. I'm just going to go ahead and do this here. Derivative of 4x is 4. And then subtraction with high d low, so 4x times the derivative of 1 plus x squared, which is really just the derivative of x squared, which is 2x, all over low squared, 1 plus x squared, quantity squared. And really, we don't need to in fact, yeah, I'm just going to do it at this point. We could simplify and look at factoring and all that stuff. But if you think about our end goal here, is that we're not actually interested in finding the derivative function here. We just want to find the slope, which is evaluating the derivative at this x value of -1. So what I could do at this point is not the prettiest thing, but it's not too bad, and it might be better than making a mistake just doing algebra to simplify things. At this point, I can go ahead and evaluate at -1. Just wherever I see x, plug in a -1. So I'm going to have 1 plus a -1 squared times 4 minus 4 times a -1 times 2 times a -1 all over 1 plus a -1 squared squared. All right, so 1 plus 1 is 2. Times 4 is 8. So I just calculated this piece right here. So 1 plus -1 quantity squared is a +1, so that gets this the 2 times 4. And then we'll have, let's see, we have negative times a negative times a negative. So it's going to end up being negative 4 times 1 times 2. So it's like -4 times -1 times -2, which is 8, all over a 1 plus 1, which is 2, squared, which is 4. This is going to be a 0 over 4. So this has a slope of 0, which means when we graph this, we should be seeing a horizontal line. So we'll keep that in mind, but with this slope of 0, I'm still going to find this y-intercept. It's just a little different So I want to find b by plugging in the coordinate. It's just that my equation of the line is y equals mx plus b, where m is 0, which means y is just b. And we have a y coordinate of -2. So the equation of the tangent line is just a horizontal line at y equals -2. So let's check this out. We're looking at the function 4x over 1 plus x squared, which looks like that. We were looking at the coordinate oh no, hold on, there we go. Our coordinate was a -1, -2. If you see here, so here's my f of x, and we're looking at this coordinate that's this local minimum value. Actually, it might even be an absolute minimum. So it's this turning point from decreasing to increasing, which means when we graph a slope of the tangent line there, it's going to be horizontal. This is what we call a critical point, which we're going to talk about more in our next section. So if I graph the line y equals -2, there's our horizontal line, and at that point it is tangent. So we're going through that coordinate and the slope matches perfectly right there. So when we take a derivative and evaluate and we get 0 out, that means there's a horizontal line right there, and typically that's going to line up with minimum and maximum values, which helps us find things we call critical values when looking at our functions.